All right, welcome to a video on how to graph for Introduction to Science, the ninth grade science class at Roseville Area High School. When you finish this video, you should be able to do the following things. 1. Be able to graph correctly for this class. 2. Know the specific features of a good graph. And 3. Be aware of some of the common mistakes when graphing. Now make sure before you watch this video that you've had a chance to read the graphing reading assignment that your teacher gave you. All right, let's get on with it. We're going to graph, as an example, some data on what the weight of a person would be at different distances from the center of the Earth. This will give you some insight into some things about weight and gravity that you might not have had, but mostly give us an example to talk about graphing. So, very first thing we want to do for a graph is give it a good title. Some kind of a title that is very descriptive of the experiment we've done. So, something like, for this, how weight varies with distance. From Earth. And of course we want to make that a little bit neat, so we're going to shrink that down so it fits over my graph nicely. Alright, the next thing that we want to do is make sure that we pick a good scale for graphing. In other words, we need to number our axes. We want to make sure we do that properly. Let me show you something that is commonly done that we don't want to do in ninth grade science. Commonly, if there's a big jump, like from 0 all the way up to 6.4, sometimes people will tend to want to do something like this and then go 6.4 and go up from there. We don't want to do that. That tends to obscure the trends that the graph will show. And I'll try to show you what I mean by that later. So instead, we want to make sure we start every graph with the corner spot there being 0. Now we need to get up to 14, so let's see how many lines we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Perfect. All right, so we'll go one line will equal 1,000 kilometers. 3, 4, 5, 6. All right, so 6. This will be 2, 4, and you don't need to number every line, but enough that a reader of your graph will get the idea. All right, the next thing that we want to do is make sure that this axis has a label. It goes something like this. This is distance from Earth center and we want that to be in thousands of kilometers. So every time we do a graph, we want to make sure that we have not only the label that tells us what we're graphing, but the units that it will be in. All right, let's go and do the next axis. This axis should always contain what's called the dependent variable. This one is the independent variable. So we vary this as an experimenter and then measure and see how it influences this. All right, so let's graph here. And again, we don't want to make some kind of big jump or anything. Here's another common mistake that is made in graphing. Students will sometimes do something like this. They'll see these numbers here and they'll think, well, we can just put this right here. So like they'll do 143. And then maybe 2 lines up, or the next line up, they'll do 227. And then 264. And then 417, 684. All right, the reason that that's not correct is that in a proper graph, to show the trend that the graph is supposed to show, each of these lines on the graph needs to represent the same amount of whatever this is measuring. In this case, we're measuring weight in newtons, so each line needs to represent the exact same number of newtons. So in this case, we don't want to do it like that. I'm going to erase this and we'll do it the correct way. All right. Another thing is we generally want to fill up most of the graph, but maybe not all of the graph with our graph. So we want to make sure that we don't sort of crowd it all down here. Now we need to go from around 100 all the way up to around 700. And let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 lines that way. All right, so it looks like we could go about 50. That will take us up to 700. So I'm going to number this one 100. That will be 50, 100, 150, 200, 250, 300. This will be 400, 500. Whoops, made a mistake there. Again, every line needs to be the same amount. 500, 600, 700. All right. Now we need, as we had here on our dependent variable axis, we need to put a label as well as units. I'm going to write it down here and then put it up here. This will be weight of a 70 kilogram person. And the units there are newtons. Weight of 70 kilogram person in newtons. Basically, whatever heading you have in your data table can be the label on your axes. All right, let me maneuver this up here so it's in the right spot. There we go. All right, now we're ready to actually start plotting our data points. So I'm going to plot in blue. Our first data points should be 6.4 and 684. So this is 7, so 6.4 is going to be right about there, and 684 is going to be way up there. All right. Our next data point needs to be 8.2 and 417. There's 8, there's 9, so 8.2 is right about there, and 417 is going to be right about there. Okay, in our next data point, we need to have 10.3 and 264. 10.3 and 250, 64 is going to be right about there. Then we need 11.1. There is 11. 11.1 is a little more than 11, but not much. And then 227 is going to be right about there. And then lastly, we need 14 and 143. And 143 is going to be right about there. All right. So we have our data points plotted, and now we need to decide what kind of best fit to put to that. All right, I brought back from the front page this list of types of graphs, types of relationships really. This relationship shows an increasing constant rate, so as x increases, y increases, but at a steady rate. This one's called an increasing growing rate, increasing shrinking rate, decreasing constant rate, decreasing growing rate, decreasing shrinking rate, and no relationship at all. So we need to choose which of these is going to be best for this graph here. And I think you can see that this has kind of a swoop to it, although not much. It could be this one, but most likely with the swoop that you see here, it's going to be the decreasing shrinking rate. So I'm going to go up and grab a line, and we're going to do a best fit curve right through that. Now when you do a best fit, let me attempt to do that one again. We want to be smooth, which I have a fairly difficult time doing with the tablet I'm working on. but we don't need to hit, it's not good either. We don't need to hit every single point. What we want is a smooth trend through the data without necessarily hitting each point, but you are welcome to hit the data points. You just shouldn't try. The key to a best fit is that you show the trend. Now, a common incorrect thing that students do is to connect the dots. For example, with the data that we just drew, students might do this, and then this, and then this, and then this. That doesn't show the general trend. That shows only the specific connection of dots that we had for our particular experiment. But what we want is a general trend. And so what we expect is that anytime we do an experiment where we look at how the distance from the center of the Earth affects the weight of the person, we're going to expect kind of a swoop to that. The exact data points might not be in the same spot, but we expect that general swoop. All right, well, we've seen this example. Let me point out a few things before we go on to our next example. First of all, we put in a good title that describes the experiment. We numbered the axes, making sure to start at 0, and making sure that every line represents the exact same amount. We made sure the independent variable was on the x-axis with units. We made sure the dependent variable is on this axis, again with the units that we measured it in. We plotted our points, and then we drew a best fit curve or line that represents one of these sort of relationships through the data points without trying to hit or miss any of the data points. Again, just to see the general trend. Let's look at another graph. Here is a graph of the year and the mean global sea level rise. So this shows how much has the sea level risen, ocean levels risen overall, kind of on average over the whole Earth since 1992. Again, I've got a title that's descriptive of my experiment. I have the dependent variable here and my independent variable here. Now in this case, year doesn't need units because it's actually the measure. Here you'll notice I do have the units that we're going to measure the sea level rise. We're going to measure it in millimeters. For your interest, there's about 25 millimeters in an inch. Now notice again on this axis I made sure to start at 0. On this axis I didn't start at 0 because really what this graph is doing is saying, or this experiment is saying, how many years elapsed and how much has sea level risen. And so this would be an odd case where you wouldn't have to start there. But in most cases, or really in all cases in the 9th grade science class, you will want to make sure to start at 0, 0. Let's go ahead and plot a little bit of this data. 1992 is where we're starting, so the sea level hasn't risen since then at that time. 1995, we want 9.8. There's 1995 and about 9.8. All right, let's go to 1999 and 22.7. There's 25, there's 22.7, 1999. All right, let's go to 2003 and 35.5. There's 35, it's just a bit over that. All right, then the next is 2007 and 48.3. 2007, there's 50, there's 48.3. And then here is 2011, and that's 61.7. Something like that. All right. Now, you'll notice that the general trend here looks very straight, what we call an increasing constant rate graph. Again, we're going to put that best fit trend in there, and this one's a little easier to do. You can definitely and should use a straight edge, and I'll give this a try here. Whoops, I missed altogether. Well, that's not such a hard thing with this computer program I'm using. We'll just rotate that right into fitting. You'll be able to do a much better job because you don't have to work on the screen. Get rid of that guy. All right, there's our nice best fit line, and and for our graph. I want to show you one neat thing that we can do with the graph, and that's to extrapolate. That is to figure out something beyond the data we took. For example, we might want to know what will the sea level rise be in by the time 2013 rolls around, which happens to be this year, and we can use the graph to sort of read up. 2013 is right there, and read on over, and we would guess that based on this graph that in 2013, 2013, the sea level rise since 1992 will be equal to, it looks like maybe 72 millimeters. So that's a neat thing you could also do. Or you can come within the data set. For example, how about in the year 1998? What was the sea level rise then? Well, it looks like just about 20 millimeters. So again, you can use graphs to make predictions. But again, the main features of the graph: title, dependent variable with units, independent variable, typically with units, proper spacing in the numbers, so every line represents the same amount, same thing here, data points plotted, and then a best fit line or curve drawn through the data set. That's the video on graphing for tonight. Thank you.